Alright, welcome back to another course. In this course, we're going to talk about electronics. And in this course, we're going to look at a few things. We're going to look at amplifier circuits, just as a generalization. We're going to look at diodes, which is a new component. We're going to look at transistors, and then field effect transistors, or FETs. And maybe the first question you ask is why even amplify anything, or what does it mean to amplify something? So if we consider a signal in time, like we have here on the bottom left, we're going to send that through an amplifier. And that signal could potentially get amplified such that there's a scaling factor from the original signal, so that we could also simply write y of t being equal to a times x of t, where x is our input, y is our output. Now if we consider why we would ever amplify anything, well, first consider the case of a satellite trying to talk to an antenna on Earth. And for this example, we're going to assume that the Earth is a sphere instead of the truly shaped donut that it really is. But nevertheless, we're going to have a signal that goes from Earth to a satellite in space. And unfortunately, as that signal propagates here on Earth, whether it be the atmosphere, we're going to see that that signal strength will decay. And the satellite all the way out here, it might only receive 0.01% of the transmitted amplitude from the antenna. Now this would be an extremely weak signal, and it may even be hard for the electronics inside the satellite to determine if this was noise or a real transmitted signal. So what we need to do is amplify. But to even understand how to amplify a signal, or how to amplify anything for that matter, we really have to see what kind of amplifiers we can even have. Now the first kind of amplifier that we have here is the inverting amplifier. So this is different from what we just looked at in the first few seconds, where the output has some scaling factor. Again, a times our input, x of t, but a can be negative. And then our non-inverting, which we saw in the first few seconds, where that scaling factor a was positive. So generally speaking, we can have an amplifier, as we have here, where it's just some general amplifier. We're going to have an input voltage and an output voltage. We can define the voltage gain, or we could just call that the gain for now, as this a subscript v, such that the output voltage is equal to that gain factor times the input voltage. Now, in terms of gain, we look at a few different kinds of gain. That would be the voltage gain, the current gain, and the power gain. Now, the current gain is represented as a subscript I, and it's not the same as the voltage gain. And then we have the power gain, and that's going to be represented by the letter G. So we know how to calculate the voltage gain up here, but to calculate the current gain, we kind of need to know some things about the system. So if we connect a load resistor, call it RL, and then we know that the amplifier has some input impedance or input resistance, RI, we can say that the current gain is equal to the output current divided by the input current, which would simply be the output voltage divided by that load resistor, that whole ratio divided by this new ratio of the input voltage divided by the input impedance or resistance. Nicely enough, that's equal to the voltage gain times this ratio of the input impedance to the load impedance or resistance. And unfortunately in textbooks, impedance and resistance for these kind of amplifiers gets used interchangeably. Now we can also look at the power gain, G, which is equal to the output power divided by the input power. And we know our relation between power, the voltage, and the current, and that's actually equal to the voltage gain times the current gain, which is also equal to the voltage gain squared. And then again, we have this ratio of the input resistance and the load resistance. So if we look at a circuit, or again, a general amplifier, right here, we have some input voltage, Vi of t, some output voltage, and then some load resistance. To break this down into a real circuit, there's some terminology that we kind of keep throughout this course. So if we have some voltage source, Vs, with some source resistance or impedance, we'll have some input and output currents, some input and output resistances, we'll have our voltage input and output, and then we're going to have this thing called the open circuit voltage gain. Now the open circuit voltage gain is not equal to the voltage gain, and we'll see what we're talking about here in a second. Now commonly, you'll see this amplifier circuit expressed as this circuit here, where kind of all of this is your amplifier. Notice here, VI of t turned into that source resistance and your true voltage source. So if we start to dissect the circuit, let's get rid of the green brackets. So if we just get rid of the green brackets, we can look at the circuit, and what we notice here is that we have a dependent voltage source, which is equal to that open circuit voltage gain, AVO, times the input voltage. We have an output resistance, and we have our load resistance. So we could say that the output voltage is equal to the voltage divider for this load resistor, which is equal to this term here. And we know if we have the output voltage and the input voltage, we can divide that to find the voltage gain that we previously defined. And notice that the voltage gain is equal to the open voltage, or the open circuit voltage gain, times this resistor combination here. Now, if the load resistor goes to infinity, you can kind of think of that as an open circuit, and the output voltage is approximately equal to the open circuit voltage gain times the input voltage. And then also, the voltage gain is approximately equal to AVO, or the open circuit voltage gain. Now, if the load resistor goes down, the output voltage also goes down because we would have a seemingly short circuit if it went to 0, and the output current skyrockets, not to infinity, because we still have this output resistance here that would limit it. And if we think about what this really tells us, well, the output voltage drops as the load resistor drops, which doesn't really mean much to us, but it does tell us that the load affects the amplification. And I think that's more meaningful, because now if we connect load 1, we get some kind of amplification, but if we have load 2, which is a different value, we amplify differently. And sometimes this might be nice to have, but ideally we probably don't want this, and we'll see more about some cases where we don't want this in the next few videos.